Captions in English, please. So this is the first video of chapter 7, and chapter 7 is on reactions in aqueous solutions. And so this first video will focus on introducing you to aqueous solutions. So an aqueous solution is an homogeneous mixture, which means it's uniform throughout. Homogeneous, remember, means it's uniform composition throughout, because it looks like one substance, but you know it's made of more than one. So an aqueous solution is a substance dissolved in water. And some vocabulary that you need to know here. A solution contains a solute, and that's the component in the minor component here in the lesser amount. And the solvent is the component in the greater amount. So it doesn't matter which one is which. What matters is the quantity. You know, the one in larger amount is the solvent, and then the one in lesser amount is the solute. For example, here we see a solution of, it's salt water. So there is a table salt dissolved in water. Solutions are homogeneous because the ratio of solute to solvent remains the same throughout the solution. So same composition throughout. So because of that, it looks like one substance, but you know it's made of more than one. So a color change, the formation of a solid, the formation of a gas, the absorption or emission of heat, and the emission of light are all visual clues that indicates a chemical reaction has taken place. So how do we know whether a reaction is likely to occur or not? How do we predict this? And so a reaction will proceed to the formation of products because there is a force that drives them to do that. And there are different kinds of force. Common forces that drive chemical reactions to occur are the formation of a solid, the formation of water, the formation of a gas, and the transfer of electron. Whenever you have one of these possibilities that can happen, then the reaction will move forward and you will have a chemical change, and the reactant will change into product. So some more vocabulary here. A compound is soluble in a particular liquid if it dissolves in that liquid. And we say that a compound is insoluble if it does not dissolve in the liquid. So soluble or insoluble, make sure you write them properly. The formation of a solid upon mixing two clear aqueous solutions together is called a precipitation reaction. So a precipitation reaction is when you have formation of a solid when you are mixing two clear solutions together. And the solid that is forming is called a precipitate, and that's why the reaction is called the precipitation reaction. And so a precipitate will come out of solution because it is insoluble in that particular solution. So it's like a powder forming inside the liquid. But the powder is a solid because if you evaporate the water, for example, the liquid, what will be left will be a solid, a powder as a solid. So for example, there is a picture here showing a precipitation reaction. We have a solution of K2CrO4, and it's the yellow solution. And it is added to a solution of barium nitrate, which is BaNO3 two times. That's the colorless solution in the beaker. And when we are mixing them, we see the formation of a yellow precipitate. It's that cloud in the beaker forming. So what is the formula for the yellow precipitate? The formula can be predicted based on the chemical reaction and a knowledge of solubility rules. So what does an aqueous ionic solution look like at the molecular level? It is important you understand that when you have ionic compound soluble in solution, you have to imagine that actually it is the ions that are floating around in the water. When a soluble ionic compound is placed into water, the ion, we say, dissociate, which means they break apart. into water. Notice that polyatomic ions do not break up into individual elements, but remain intact. Here in the example, we have two polyatomic ions, the chromate, CrO4 2-, it stays as that, unit made of one chromium ion, one chromium atom and 4 oxygen atoms, and then the overall unit has 2 negative charges. And then in the barium nitrate, there is the nitrate NO3 -1, and that's another polyatomic ion. And so we know that these ionic compounds dissociate into ions because the solution conducts electricity. They have been tested and they conduct electricity, which means you have charged particles floating around in the liquid. And those charged particles are the reason why they can conduct electricity, because they can float around and move from one, to each electrode, depending on the sign of the charge. And so pure water, for example, does not conduct electricity. It's not an ionic compound. It's a molecular compound that is neutral. So pure water does not conduct electricity. And so there are some insoluble ionic compounds in water. Not all ionic compounds are soluble. Not all ionic compounds are soluble in water. And so, for example, AgCl does not dissolve very much in water. So here you see a piece of crystal at the bottom of the beaker, and then you see some ions, but very few, very, very few. And so it is considered insoluble, even though a very tiny amount dissociates. So you see, very few ions, but mostly it's the crystal, at the bottom of the beaker. So even though there is a tiny amount that dissolves, we say it's considered insoluble, because AgCl remains mostly as a solid within the liquid water at the bottom of the beaker. And so this would be considered insoluble. What is a strong electrolyte? An electrolyte is a liquid or gel that contains ions and can be decomposed by electrolysis. For example, potassium chromate or barium nitrate solutions do not contain any K2CrO4 units or BaNO3 two nitrates per barium units. They do not contain those units. What they contain is potassium ion, K+, the chromate ion, CrO4 2 negative charges, Ba2+, and the NO3 -1 ions. So it's individual ions that are floating around in the water. So we said those substances like K2CrO4 or the barium nitrate, we say that they completely dissociate, 100% completely dissociate into ions in solution. And because of that, we are calling them strong electrolytes, because they are, completely becoming ions. All soluble ionic compounds are strong electrolytes. Whenever they are soluble, then there will be strong electrolytes. Some molecular compounds are also strong electrolytes, like strong acids, like H2SO4 and HCl are also strong electrolytes, which means they dissociate into ions. And in the case of acid, it would be H+ ions, and then here in the example of H2SO4, the sulfate ion, SO4 -2, or in the case of hydrochloric acid, HCl, it would be H+ and Cl-. So we also have what we call weak electrolyte. And so that's the substances that partially dissociate into ions in solution. And example of weak electrolytes are ionic compounds that are classified as being insoluble in water based on the solubility rules. We will see them later on in this chapter. And so, for example, HgCl, silver chloride, is considered insoluble. Calcium sulfate, magnesium carbonate are all considered insoluble according to the solubility rule, and they will be a weak electrolyte. Because even though we classify them as being insoluble ionic compound, a very small portion of the ionic compound still dissociates. So there is some ions, floating around, very few, compared to the strong electrolytes, but there is some. So that's why we call them weak electrolyte. Some molecular compounds are also weak electrolytes. For example, weak acids like HF, hydrofluoric acid, or HC2H3O2, which is acetic acid. These are also called weak electrolyte because they are weakly dissociating into H plus ions and then F minus for hydrofluoric acid, or H plus and C2H3O2 negative 1, the acetate ion for the acetic acid. And then there is the non-electrolytes. Substances, mostly molecular compounds that are soluble in water but that do not dissociate into ions in solution are called non-electrolytes. A typical example is sugar. Sugar is glucose, and it's an example of a non-electrolyte. Sugar, C6H12O6, is made up of covalent bonds and therefore will not break apart into ions when it is dissolved in water. It will stay as the big molecule with all its bonds still intact. And there is no charge, no positive or negative charge. So it's gonna be a non-electrolyte because of that. So let's look at a simulation here from PHET Colorado. So let's look at the simulation here where we have solids that can be salt or sugar. So if I shake the salt here to distribute some salt into the water, now I want to see the values, and I have some salt in the water now. So let's look at the conductivity of the solution. And here the light bulb is on, it's turned on, and that means this solution of salt and water is conducting electricity. Let's look at what it is at the microscopic level. Let's pour some more sodium chloride. So here it's showing the chloride ions as green balls, the sodium ions as pink balls, and you see how when they fall into the water, they completely get free from each other, all free from any other ions, and they are, moving around in the water. And so now if we look at the water level and put some salt in there, you will see how the ions are, taken apart from each other, and then they are surrounded by molecules of water. So now let's look again at this, but with the sugar. So this time we'll pour some sugar in the water. And let's look at the conductivity of the solution. And here let's look at, do we have enough sugar? Even if we put more, you can see that the light bulb is not lit. It's because this is a non-electrolyte. Sugar is a non-electrolyte, so it will not conduct electricity. Now, at the microscopic level, if we put some sugar, sucrose actually, it's not sugar, it's sucrose, C12H22O11. And so it's a big molecule made of carbon, hydrogen, and oxygen. And you can see that they are staying bonded together. The molecule, stays as it is, and they are free from each other, the molecules, but the molecules does not break apart, does not make any kind of ions. And so that's why it's not conducting the electricity. And now if we look at the water level and put some sugar in there, You know, it's a big molecule here. It's all in yellow, but it's actually made of carbon, hydrogen, and oxygen. And you can see how, you know, at first, when it's in the solid phase, it's together, bonded to, you know, held together. The molecules are held by intermolecular attractive forces. But then in water, the water surrounds each molecule, and that's how it dissolves in water. And so you can see that this is also represented here in the on the right side of the slide, how sugar, you know, at first is solid, and then the molecules of water come pick up one molecule at a time and then surrounds the molecule by, you know, molecules of water. And that's how sugar gets, you know, dissolved in water. It starts on the surface until all molecules have been surrounded by molecules of water. And so this represents an experiment where we have solutions. On the left, we have a non-electrolyte solution, and it's represented by a diatomic molecule with two blue spheres there. And even though you try to have a circuit and an electrical current going through this, it doesn't work. The light bulb is not lit because it does not carry the electricity between the two electrodes. In the case of a weak electrolyte, we have some ions, and most of the molecules are not dissociated into ions. So the very few ions that are here are trying to conduct the electricity, but it's a very weak light from the light bulb because there's not enough current there. And then in the case of a strong electrolyte, we see how the light bulb is brightly lit because there is only ions, you know, in water, and that allows the current to be fully conducted between the two electrodes, and then the light bulb can be lit. So if ionic bonds are so strong, then why do ionic compounds dissociate when we put them into water? So why do ions form? Let's look at a video that will explain this briefly.
Sodium chloride crystals are held together by attractive forces between the positively charged sodium and negatively charged chloride ions. When a crystal of sodium chloride is placed into water, the hydrogen ends of polar water molecules attract the negatively charged chloride ions and gradually surround them. Likewise, the oxygen ends of water molecules are attracted to and surround the positively charged sodium ions. The hydrated ions drift away into the solution, allowing new water molecules to surround newly exposed ions. Gradually, the entire crystal dissociates into solution.